This is Introduction to Proofs, section 3.4. Today is April Fool's Day. But we are not fooling around. We are hitting the preview activity 1 right away. So preview activity 1 says we want to do a truth table to show that P or Q implies R is equivalent to P implies R and Q implies R. I think I'm going to use a Word document to do this one because it's just a lot of truth and false things to write down and it's going to get tiring. So let's make me smaller, like this, maybe the right size. There we go. All right, and then maybe zoom in a little bit. Let's insert, we need a truth table with, let me think. We need a lot of things. So we need P, Q, I'm just going to use all of them and we'll see where how things line up. I need a bunch of rows too, probably more. All right, so I need P, I need Q, I need R. And we can kind of make those over there. Okay. And then it's pretty standard that you do divide the first column, you do like half of them are trues and half of them are falses. And I need an extra line. So insert below false. And then you do true, true, false, false, true, true, false, false. And the last column you do true, false, true, false, true, false, true, false. You don't have to do it this way. It's just the way that most people do it. So then I'm going to do P equals P V Q, and then that's more than I need right there, and then I need equals P, nope, parentheses, P, V, now notice the spelling V-E-E, Q, Q, R, and that'll complete the first thing. And then I'll need to do the other one, I need to do two parts. Alt equals P, R, and then it's then Q to R. And then this P to R, wedge Q to R. And apparently, that's an extra column I didn't need. So delete column, delete column. Right. So let's put my caps lock on, get my fingers on my true and false. Let's go. So P or true. So here, P is true for all these four, and Q is true here and here. And it's only when they're both false that it's false. Okay, now P or Q implies R. So when R is true, this will be true. And when P or Q is true and R is false, it's going to be false, false. So here, P or Q is true and R is false. But here, P or Q is false, so it's vacuously true. Okay, so then P implies Q. So P implies Q. It's going to be true when Q is true. And it's going to be false here because P is true but Q is false. Then here it's going to be vacuously true. So vacuously true. And then Q implies R. It'll be true for all the true values of R. And then when Q is true but R is false, it'll be false. And when Q is, here's Q is false, so it's vacuously true. And here Q is true, but R is false, so it's false. And here it's vacuously true. And then I gotta and those two statements. So true, but that one's false. That one's false. That one's false. That one's true. False, true, true. Okay. They're not matching up, so did I make a mistake? Very likely. Let's see. So we have P or Q is true, 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 false, false. And P or Q implies R. So it's false, true, true, false. So here P or Q is true, but R is also true. So if R is true, then this one is true. Ah, found it. All right. So then that makes that true. So then we've got true, those line up, falses, trues, falses, trues, falses, trues, and trues. Yeah. All right. So I'm going to make these ones bold and these ones bold because the ones I'm comparing, they are the same. As maybe I'll make the top bold too. All right. So that completes number one. Suppose you're trying to prove a statement that is written in the form, basically trying to prove a statement that's written in this form. Why can you do a proof of this and then a proof of this? Well, because they're logically equivalent. So if I'm trying to prove this thing, proving this thing would be assuming P or Q and then proving R. And you can really do P implies R and then do another proof of Q implies R. Okay, that's it. Explain what statement, if n is an integer, then n squared plus n is an even integer, is logically equivalent to if n is an even integer, then n squared plus n is even, and if n is odd, then n squared plus n is even. It's exactly the thing. It's really, really leading the witness here. So here P would be n is even, Q would be n is odd, and R would be n squared plus n is even. Okay, so in the beginning, the first statement is if n is even or odd, it's just an integer. Okay, but here you can do P is even and it's true, and then proof when P is odd and it's true. So it's true for all the integers. Okay, that ends preview activity number one.